Thank you very much, Marcus. Thanks for the invitation to come here. It's always a great pleasure. I've been here lecturing at schools a number of times. I also used to work here, as Walter, I think, kindly reminded me as to how old I am. I was organizing a school here when he was a PhD student in 2001. And well, I might say not exactly the same stuff as what I told people back then, but parts of it, of course, will be more or less the same. So neutrino cosmology, you heard a lot about it already, sort of in various contexts. But the point is that first and foremost, of course, neutrinos are super important for how the universe develops. So they're important for structure formation in our universe. They're important for Big Bang nucleosynthesis. And the fact that neutrinos are so important for our universe also means that we can reverse the argument and use cosmological observations to probe neutrino physics. And of course, as you've heard a lot of stuff about, neutrinos are indeed very, very hard to probe. So we know very little about neutrino physics compared to many other types of particle physics still. So let's get started. Oops. Okay, hang on. So today, that will be the basics. So what I'll be assuming is that we are living in a completely homogeneous and isotropic universe. So we're assuming that the universe obeys the cosmological principle. So everywhere is the same. That will, as you will see, simplify things quite a lot. Of course, we also know that this is not true. We know that our universe is very, very far from being homogeneous and isotropic. However, the early universe, at least when we observe the microwave background radiation, is known to be almost homogeneous and isotropic to 1 part in 10 to the 5 or so. Strictly speaking, we don't really know if that argument holds in the very early universe, because the scales that we can probe, as you'll see tomorrow and Friday, using cosmological observations, are on a much larger scales than what would be relevant in the early universe. But everything that we observe is consistent with the universe being very close to homogeneous and isotropic early on. So we'll talk about the basic cosmological equations. Some of you will presumably know this quite well already. Then I'll go on to talk about specifics of neutrinos, and this is related to neutrino thermodynamics or statistical physics, neutrino decoupling in the early universe, and so on and so forth. I'll talk about bounds on neutrino masses from very simple arguments. So these are bounds that have been around for many decades by now. The nice thing about this is, if you're interested in dark matter, for example, many of the arguments that were initially developed for neutrinos carry over to WIMP-like dark matter, for example. So if you want to understand the freeze out of particle physics, dark matter candidates, then neutrinos are a good place to start. Then we'll talk about Big Bang nucleosynthesis and how you can probe neutrinos using BBN.
So there should be, yeah. Let me stop sharing for a second. I apologize.
Okay, very good. And so as an example, I'll just use BBN observations to give a constraint on the number of neutrinos that are around in our universe. And as you'll see a little bit later, what I mean by neutrinos in this context is, in fact, just any type of light particle species. Neutrinos are just a prototype, but it could be axions or many other types of particles. Okay.
Always at the beginning.
Yes. Okay. Then tomorrow and Friday, we will relax the assumption of homogeneity and isotropy, and I'll talk about structure formation. This is really where most of modern day neutrino cosmology is located. That is looking at how neutrinos influence the formation of galaxies, galaxy clusters, and so on, and how you can conversely use this influence to constrain the value of the neutrino mass. And as you'll see, the bounds that we get from cosmology are roughly an order of magnitude better than what you can do using laboratory experiments. I'll talk about future observations. Maybe I will talk about sterile neutrinos. We'll see how far we get. And let's see how this works. Yes. And of course, this again is something that you've seen a number of times already. So these are just the various places in which we can observe neutrinos in nature. Reactors, the sun, we can create them not just in reactors, but also in accelerators. We have them from supernovae, we have them from AGNs, and of course, high energy cosmic rays create lots of neutrinos that are called atmospheric neutrinos. We even have these geoneutrinos coming from the Earth's crust. And the only place, in fact, where we really haven't directly observed neutrinos is the cosmic neutrino background. So this, of course, is where most of the neutrinos in our universe are. So it's equivalent to the cosmic photon background, which has been observed, of course, for decades. The problem is, as I think was also alluded to by Gabriela, is that it's next to impossible to observe directly. If you calculate the cross section, it's just ridiculously low. Maybe we'll get back in 1 or 2 minutes or so to possible ways of actually detecting this cosmic neutrino background directly. But the point is that since it's a weak interaction, cross sections typically go as energy squared. And since the energy of a cosmic background neutrino is of order 10⁻⁴ electron volts, the cross-section is ridiculously low. So you have to borrow energy from somewhere. And for example, doing neutrino capture on tritium, for example, so instead of just having the ordinary tritium decay, just having a neutrino capture reaction, you can sort of borrow the Q value of that reaction, and that might, in principle, at least in the future, allow us to do a detection of this background. We do know it's there. As you'll see later, we have an indirect detection at something like the 10 sigma confidence level. So we know for sure that the cosmic neutrino background is around, but we cannot see the particles directly. Okay, so getting to the cosmology part. Now, of course, starting from just GR, we would start from a line element of some sort, and we would have a metric tensor. And the question is, what would we put for this metric tensor? We know that the Schwarzschild metric pertains to, for example, our solar system to a very good approximation. The assumption that we will be using today is that the universe is homogeneous and isotropic, and that simplifies life tremendously. It means that we can write the line element something like this. Of course, that's just one possible choice. But the point is that the only parameters that are relevant to an expanding universe in this way of writing it is this so-called scale factor, which tells us how the spatial part of the metric expands or contracts as a function of our time parameter. And the scale factor can be a function only of time. Of course, it cannot be a function of location, because otherwise we violate homogeneity and isotropy. Then there's one additional thing that we have to worry about, and that's the global curvature of the metric that we're working in. So it could be either a Euclidean space that expands or contracts, or it could be a curved space that expands or contracts. And all the possibilities for simply connected metrics are shown here. So we basically can have positive or negative curvature, or we can have a spatially flat Euclidean metric. And observations point us in the direction of something that very well approximates the flat Euclidean space. Of course, that's not to say that the universe or the metric is strictly flat. It's just that the radius of curvature of whatever metric that we are living in is very, very much larger than the observable universe. So to a very good approximation, the spatial part of the metric is just Euclidean. And the only thing then that is relevant to us is the scale factor, so how the universe expands or contracts. Now, in order to get an equation for the scale factor, we would need the dynamics of the theory GR in this case. So we would need to go to the field equation. where we have the Einstein tensor on the left-hand side, and we have the stress energy tensor on the right-hand side, plus this possible additional term, which we normally call the cosmological constant. We can, given that the universe is homogeneous and isotropic, simplify this very, very much. So in fact, there are only two independent differential equations hidden inside this much larger system of equations. And the 0-0 component, the time-time component of the Einstein equation, is actually what we normally call the Friedmann equation. So that is an equation that tells us how the logarithmic derivative of the scale factor responds to whatever stuff you put in the universe. So whether you put matter or radiation, or you have, for example, this cosmological constant, or you have a curvature of the metric, all of these things can be thought of as source terms in this differential equation. Of course, that's just a way of writing it, so to speak, because, for example, the curvature here is really a term that originates in the metric part of this equation over here on the left-hand side. However, traditionally, it's moved to the right-hand side, so you can even think of it as a source term for expansion. If the universe is curved, you change the expansion rate of the universe. Normally, we also, given our complete and total ignorance of what this cosmological constant is or might be, we just absorb it into a generalized energy density, which we can just call rho tot. So this is not necessarily energy density associated with normal fields in the traditional sense. It could be energy density associated with this cosmological constant term. It just behaves very differently from normal types of energy density. So the standard cosmological model, the one that we call the lambda CDM model, which has been tested quite rigorously in the past 2 or 3 decades, contains 3 different terms. It contains a matter term, which is baryonic matter, and dark matter, which in this context is just assumed to be always completely non-relativistic particle dark matter. And by non-relativistic, I don't necessarily mean heavy particles. It could also be axions, for example, but something which in the general relativity sense of the word has no pressure. So there's no kinetic energy, so to speak, associated with the matter. And then we have radiation, which in the simplest form is just non-relativistic particles. Of course, neutrinos are known to be neither here nor there, right? In the sense that we know that neutrinos have mass, they just have very small masses. And that means that neutrinos can in fact be both matter and radiation, depending on at which time you look at them and what type of neutrino we're talking about. And then there's this additional lambda term that actually from observations seem to make up about 70% of the total energy density in our universe. Now, if we look at the different types of matter, we realize something else, which is actually in the end quite nice, because it points to separability, so to speak, of this term, in the sense that the matter term scales with the scale factor as 1 divided by a cubed, for a very simple reason. You just think of it as a collection of particles. You put it inside an expanding box, and the density of particles, of course, scales as 1 divided by volume of the box. And that's all there is to it. However, radiation is different in the sense that if you have a collection of particles that are not dominated by the rest mass term, but also have a kinetic term, if you solve the geodesic equation for a free particle, then you realize that the physical 3 momentum of that particle always scales as 1 over the scale factor. That means that any particle that moves around in our universe, if we assume that it's just homogeneous and isotropic, loses momentum with time. So this, of course, is well known for photons. We know that they redshift, but in fact, it happens to any particle that moves around in our universe. So since photons, their energy is dominated by the kinetic term, we get an extra factor of a, so that the energy density scales as 1 over a to the power 4. And then we have this cosmological constant term, which indeed, as the name implies, turns out to have a constant contribution to the energy density, which is super weird. And as many of you probably know already, of course, if you associate it with a fluid, that would require you to have a negative pressure of that fluid. So it's something very, very non-standard. Okay, so if we look at just the radiation, one thing that we can also realize readily from this is that since the energy density scales as 1/8⁴, and we know that the energy density in a photon gas or a gas of relativistic particles scales as temperature to the power 4, we would, from these very simple reflections, get that the temperature goes as (8⁻⁻1). So this would be true, of course, for a distribution of photons in complete thermal equilibrium. Actually, it's also true, as it turns out, for photons that are completely out of equilibrium because of this redshifting effect. And that means that when you look at the cosmic photon background, for example, you can't actually tell whether it's in thermal equilibrium or not. I mean, normally you wouldn't think of a collection of particles out of thermal equilibrium as even having a well-defined temperature, right? That shouldn't be the case. That only exists in an equilibrium sense. However, because of this redshifting effect, we actually find that temperature is a good descriptor of the photon, or neutrino for that matter, statistics, even outside of equilibrium. So that's something worth bearing in mind. Okay, very simple. Also, we won't be using it today, but tomorrow we'll talk about cosmological observations, and astronomers really, really like this parameter called the redshift, which probably you more or less all know. This is just an observations-related parameter dating all the way back to Hubble's time, that if you observe a wavelength of some sort and you relate it to the emitted wavelength of whatever line you're looking at, then the shift is given by the redshift. That's basically it. But since this shifting comes from the loss of 3 momentum of the photons, you can relate it to the scale factor at the time of emission. And in that sense, it's a really, really nice parameter because it gives you a one-to-one correspondence between this redshift and the size of the scale factor at the time where the photon was emitted. Okay, so this is the separability. And it's actually quite nice because it simplifies life tremendously. Now, if you want to solve the Friedmann equation, this differential equation for the scale factor, the more complex the source term on the right-hand side, the more difficult, of course, it becomes to get an analytic solution. However, because we have this different scaling of the different components in our universe, what we can see is that except for 2 crossing points, the universe is always dominated by a single type of energy density. For example, the early universe, which is where we'll spend most of the time in this lecture, is completely dominated by radiation. So to a very good, and this would be true even in a curved universe, I should say. I didn't plot the curvature component, but actually the curvature component, as you go back in time, also becomes less and less and less important. So almost no matter what the current universe looks like, the early universe is super simple. It's just a radiation-dominated flat universe. And that means that all the equations for the scale factor and the relation between time and temperature and so on are very straightforward. Then once we go to this phase here, the universe has a phase where it's completely matter dominated. That's very important for us because had that not been there, we would not be here to discuss it. All structure formation in the universe, as we'll see tomorrow, has to happen in the matter-dominated phase of the universe. You cannot have structure formation in a universe that's dominated by radiation or by a cosmological constant or by curvature, for that matter. Then the current universe is lambda-dominated and presumably will remain so forever, at least in this very simple model, given that we don't know what this cosmological constant or dark energy term is. Of course, there's no way at the moment of telling whether that's true or not. Okay, so the early universe, as I said, the early universe is just a radiation-dominated flat universe. And we can do thermodynamics in such a system. Now, I just start from the one particle distribution function without actually qualifying whether that's a good approximation to how to describe neutrinos or not. So if you have a normal, simple statistical physics system, you should be able to describe the number of particles in a given momentum state using this distribution function. Of course, that would also normally be a spatially dependent function because different places in time, in space, might have different distribution functions. But given that we're in a homogeneous and isotropic universe, we only have this distribution function. Of course, why are you allowed to use this description, you might wonder, right? Because after all, we have not qualified in any way whatsoever whether we should be using a more complex description of the system. For example, are we really sure that such a thing as truly free particles exist in the system, or are they continuously interacting? For example, one would have to check whether that's actually okay. And as it turns out, and this is something that is maybe a little bit hard intuitively, what turns out to be the case is that our universe is always, from this point of view, super duper empty. Of course, our current universe seems to be very empty. We seem to have very long mean-free paths of photons, for example, and so on. But even if you go to the very early universe, it's still true in the sense that if, for example, you have a neutrino or a photon or whatever, a particle, then you can, to a very good approximation, think of it, at least for neutrinos, let's stick to them. You can think of the system as consisting of free neutrinos that then every once in a while interact with something, and then they go on and do something else. And that means we're actually allowed to use this description. Of course, in principle, one thing that we should do is to allow for example, neutrino oscillation. So really, we shouldn't have these one particle distribution functions for neutrinos. We really should be having a density matrix that would allow us to look at how neutrinos, for example, oscillate. It will be important for some particular calculations, but not for the overall picture. So I'll just stick to this distribution function description. Now, in equilibrium, well, in full thermal equilibrium, we would have only one parameter that fully describes this distribution, namely the temperature. And if you don't have full thermal equilibrium, I'll get to that in a minute, then we might also need a chemical potential for the system. And if you have very massive particles, if you plug in here the dispersion relation, so you have a mass term and a momentum term, then unless the chemical potential becomes very large, what happens is that as a particle goes non-relativistic, it will vanish. So if we have a universe that consists only of particles in equilibrium, only massless particles at any given time will be around in that universe. And that's simply because, as I come to here, it's simply because that's the way you maximize entropy, right? So if you calculate the entropy of the system and you maximize it, then you find that you should always have zero chemical potentials, and you should never have any massive particles around. As soon as when the temperature drops, when the universe expands, as soon as a particle species becomes massive in the sense that the kinetic term and the rest mass term become comparable, then that particle will automatically vanish into whatever it can perannihilate into. So only if you somehow switch off these interaction channels can you have particles that are massive around in our universe. So that's, of course, something important to bear in mind, that as our universe cools, it becomes progressively simpler and simpler in the sense that you have fewer and fewer particle degrees of freedom around in the universe. Okay, so in full thermal equilibrium, and this is actually something that Gabriela talked about not so long ago, in full thermal equilibrium, if you're allowed to change all parameters of the system in the sense that you can freely change the number of particles, then you should always have a zero chemical potential, and that would mean that particles and antiparticles appear in exactly the same number, and you cannot have a baryon asymmetry. So only if you break thermal equilibrium is a baryon asymmetry, or a lepton asymmetry for that matter, allowed. So just a small note, and of course you heard this very nicely from Gabriella just an hour ago or so. In order to ever generate an asymmetry, and this is not just a baryon or a lepton asymmetry, it could be any other type of asymmetry. You need, of course, to have a process that, for example, for a lepton asymmetry, you need a process that is lepton number violating. Then you need CP violation, but very importantly, you also need deviation from thermal equilibrium. And schematically, I think this is something I stole from chemokinoline 20 years ago. It's actually a very nice way, I think, of thinking about it. This is really something that was cooked up for, I guess, gut baryogenesis, right? You have some very, very heavy gut scale particle that decays, and it violates lepton number, it violates, or baryon number in the original case, and it violates CP. So what does that mean? It means that you have these two decay channels, and one is just way more efficient, or even a little bit more efficient than the other. That means that you have these two bathtubs here, and you fill up this one quicker than you fill up this one. However, if you let it run until it equilibrates, of course, you just fill up both bathtubs, and that's it, right? You have equal numbers of all particles again. So you need to switch off these pipes here at some point where you have not yet fully equilibrated the system. And the nice thing about cosmology is that it provides a very natural way of breaking thermal equilibrium because of the expansion. So as you'll see, for example, for neutrinos, but that pertains to many other types of processes, they are typically in equilibrium in the early universe, and then they decouple from equilibrium at some later stage. Okay, so if we stick to this standard radiation-dominated early universe, the Friedmann equation does become very simple. It just looks like this, where this is the radiation content of the universe. In equilibrium, we can calculate the energy densities for bosons and fermions. They're slightly different by a factor of 7 divided by 8. And then we just sum up whatever we have around in the universe. That's it. And this is a figure for the effective number of light degrees of freedom that we have around in the universe as a function of temperature. And here you can very quickly see that, I think I have it in table form here, that as the universe cools off, less and less particle degrees of freedom are relativistic. So starting up here with the top quark, and okay, so this figure is, or this table is old because apparently the Higgs mass is lower than the top mass. It doesn't matter, right? So the point is just that as the universe cools, we have less and less and less degrees of freedom around until we reach the MeV scale, where initially we have electrons and positrons, neutrinos, and photons. And that's it, basically. Then, of course, we have baryons and dark matter, but very little, and not enough to have any particular influence on the expansion rate of the universe. So we can also solve the Friedmann equation and this is something that is always a good thing to sort of remember at the back of your mind somewhere, that there's a relation between the expansion timescale of the universe and the temperature of the universe in MeV, which basically says that the age or expansion timescale of the universe in seconds is roughly equivalent to the temperature of the universe to the -2 if you do it in units of MeV. So that means that if we look at the MeV scale universe, it's typically of order a second or so old. So that sets the time scale. Okay, so if we go into a little bit more detail, thinking about neutrinos. Of course, neutrinos are not necessarily, and that of course is true for any other type of particle, they're not necessarily in thermal equilibrium, right? And for example, if a particle is out of thermal equilibrium, there's no way that it can transfer all of its energy density to any other species, because the annihilation channel is typically switched off at that time. So you have to solve, rather than these very simple equations, you have to solve the collisional Boltzmann equation. So this is what you're always faced with. And this is true for neutrino physics. It's also true if you want to do a calculation of the number density of WIMP particles or any other such calculation. You have a left-hand side which originally was just the total derivative of the distribution function with respect to time. Then you write out all the terms. There are spatial derivatives and there are momentum derivatives. Most of them die because of homogeneity and isotropy, and only two terms are left. One which is the explicit time derivative here, and one which is a derivative with respect to the magnitude of momentum, because remember, the momentum changes as a function of time, and also the distribution function can be dependent on the magnitude of momentum, and typically is dependent on the magnitude of momentum, but not the direction of momentum and not the spatial location. So typically one splits the collision operator here on the right-hand side into two terms, one which is elastic collisions, and an elastic collision can change the momentum of a particle, but it cannot destroy or create a particle. So that can create what we know as scattering equilibrium. And scattering equilibrium is the case where you have a well-defined temperature, but since you cannot freely change the number, you have a chemical potential as well that you need to worry about. Then we have the inelastic collisions, which are typically the ones that we're actually interested in, because they are the ones in the end that tell us what the number density of particles ends up being, because inelastic collisions can change the number of particles. And in most cases, and this is something that is always, more or less at least, assumed without often saying so explicitly. Normally, elastic collisions are assumed to be much more important than inelastic collisions. And the reasoning goes like this. So imagine that you have a massive particle. We'll see examples of it in a minute. But imagine you have a massive particle that is per-annihilating with corresponding antiparticles. And they are in thermal equilibrium. But since they're massive, they have this Boltzmann suppression. So the number density is already quite low. In order for annihilation to proceed, it has to meet up with another of these massive Boltzmann suppressed particles. And that becomes progressively rarer and rarer. However, elastic collisions can happen with any background medium particle. And these are typically relativistic particles, which are much more abundant. And therefore, usually, at least to a good approximation, one can just assume that this occurs in complete equilibrium, and this is the operator that we're actually interested in. That simplifies life quite a bit, but of course you can just brute force solve everything if you really want to. Okay, so of course it's always worth, rather than solving brute force equations, it's always a good thing to try and figure out whether there are any simple back of an envelope calculations that one can do that would make life simpler for you. And one thing that one can very quickly do is to get an estimate of the reaction rate of a given particle species. So imagine you have a particle species, let's call it X, just to call it something. And we calculate what is the probability per unit time for that particle to interact with something. Well, that's just the collision operator integrated over momentum space to average. And then we get out this expression here, which is really just, okay, it's the number density of particles that you can scatter on times the cross section times the velocity. I mean, it's kind of trivial in some sense. And then there are these averaging brackets here because we do a thermal average. We average over all particles in the medium to get an estimate of what is the average time between collisions. Now, what should you compare this interaction rate to? Well, as in any other system, you have to compare it against some time scale. And the only time scale in this system is the Hubble time. It's the only time scale that exists in the background. So you compare it to the logarithmic derivative of the scale factor, which has dimension 1 over time, same as this gamma. And if gamma is very large compared to the expansion timescale, then the system is always able to maintain equilibrium as the universe expands. However, if gamma becomes small relative to the Hubble parameter, that's no longer the case. The expansion rate dominates, and the system is no longer able to keep up with this. So the Hubble parameter, like we discussed before, can be very easily expressed in this type of system. It just scales as temperature squared. And 1 divided by m Planck, that's just the 8 pi g that sits in the source term rewritten to energy units. So turning finally to standard model neutrinos, if you plug in neutrino interactions here at low energy, and here I mean MEV type energy, neutrino interactions, of course, are super well described by Fermi theory. And we know that the cross section basically goes as G Fermi squared times the center of mass energy squared. And what's the center of mass energy of this type of interaction? Well, it's approximately the temperature, because the kinetic energy that you have in the particle is proportional to the temperature. And that means that we can roughly express it as G Fermi squared temperature squared. The number density of light neutrinos, for example, is given by the temperature cubed. And that's we can compare to the Hubble parameter, and then we find a decoupling temperature of approximately 1 MeV. In the exercises, you will see that it's approximately 3 MeV, but it's in that ballpark. Now, one thing, of course, that one should realize, which turns out to be really quite important, that is that this decoupling temperature is higher than the electron mass, but it's not much higher than the electron mass. So to a first approximation, one might say, okay, but let's assume that it's just higher. Then what happens as we lower the temperature after neutrinos have stopped interacting? Well, at some point, the electrons become non-relativistic. When the electrons become non-relativistic, they will pair-annihilate into whatever they can pair-annihilate into. And that's something is photons, because neutrinos no longer interact. And that means that all the entropy that sits in the electron-positron plasma is dumped into the photons. It cannot go into the neutrinos. The neutrinos just sit in a separate sector that is non-interacting. And therefore, the neutrino energy density just scales as 1 over scale factor to the power 4. That's no longer true for the photon energy density, because energy density is pumped from the electrons and positrons into the photons. And by using a simple entropy conservation argument, saying that, okay, entropy is conserved in the E plus, E minus gamma sector because everything is in equilibrium, that means that entropy before and after is the same. And therefore, you can actually calculate how much of an entropy of a temperature increase would you expect. And what you find is that that's approximately given by this ratio here. So photons are heated relative to neutrinos. And that means that the neutrino energy density becomes much, much smaller than the photon energy density. So actually, I haven't talked about this, but that's an important thing to bear in mind. This argument would hold for any type of light particle. And if we just go back a few slides to here, for example, then let's imagine that we have some beyond standard model new particle, I don't know, like Myron or whatever, something. That decouples at a much higher temperature than neutrinos, say 1 TeV even. At the TeV scale, we have a huge number of degrees of freedom in the standard model. Now, all of these degrees of freedom eventually end up in the photons. They have nowhere else to go. And that means the photon temperature relative to that new relic that we were interested in is increased by a very large factor. And that means the energy density around in particles that were once in thermal equilibrium becomes very, very small relative to that in photons. So unfortunately, even though presumably, we don't of course know, but even though presumably there are light degrees of freedom that were in equilibrium at very high energy scales, they become extremely hard to see at low energy scales because the number density and energy density is so suppressed. However, it might not be completely impossible, and you'll see tomorrow or Friday that the bounds that we can actually get on the relativistic energy density in the universe from observations is almost good enough that we can start to see some of these very early decoupling relics. So that's another possible avenue to beyond standard model physics that in the future might be interesting. Okay, Now, even though we have this simple calculation of the neutrino to the photon temperature, in fact, of course, life is, as is usually the case, more complicated. And since the neutrino decoupling temperature is not much higher than the electron mass, that means that a little bit of energy density actually does go into neutrinos, and that increases the energy density in neutrinos by something like 0.04 or thereabouts. And that can possibly also be measured in future observations. So this, as said here also on the slide, this is actually a composite of this incomplete decoupling effect plus QED corrections to the photon propagator at the MeV scale. This 0.04 is just at the borderline of what can be detected. So in principle, in a few years from now, we could actually be probing, thermal field theory at the MeV scale and this incomplete neutrino decoupling in the early universe. So that's quite nice. Okay, so what can we say about neutrino properties given what we have already? One thing that we can say is that if we look at standard model neutrinos, we can calculate their contribution to the energy density of the universe. It's very, very simple. We know what the number density is because we know the neutrino energy density, we know the neutrino temperature, and therefore we can just plug that in. The only thing we don't know is the neutrino mass, or at least let's say we don't know the neutrino mass. Then we can actually calculate the contribution to this cosmic density parameter that I think I did not define before, but which is just omega is defined to be the energy density divided by what is known as the critical energy density, which is just the total energy density at a given time in a flat Friedmann-Robertson-Walker universe. And if you wanted the definition, is 3h squared divided by 8 pi t. So that's how you get it. The point is that omega in a flat universe is 1. This little h, which is the dimensionless Hubble parameter, h squared is about 0.5 roughly, right? So we can actually deduce a bound on the neutrino mass just from this argument, saying that, okay, neutrinos should not overclose the universe at least. That would give us a bound of something like 30 electron volts. And that doesn't seem very impressive because we know that neutrinos are way less massive than 30 electron volts. But back when this bound was first concocted in the late 60s, this was way, way, way better than any experimental bound on the neutrino mass available. And I remember when I started as a PhD student, I think there was a bound on what you would call the effective tau neutrino mass of something like 18 MeV, just to give you an example. So this was orders of magnitude better. However, okay, that's just for very light standard model neutrinos. So what I'll show you now is really something slightly different and not included in the standard model. Let's assume that neutrinos are much heavier than the MeV scale. What happens then? It's still the same Boltzmann equation you should solve. And I should say that the main reason why this line of argument is interesting is that a very massive neutrinos is just a prototype for a WIMP particle. So you could replace it with your favorite, maybe not supersymmetric WIMP candidate, but other WIMP candidate of whatever type you are interested in, and do the same calculation. Now, the Boltzmann equation for a very non-relativistic particle, assuming the scattering equilibrium, can be shown to have this very simple form, and I won't bore you with the details, but the point is it's fairly easy to grasp what is going on. So there's an explicit time derivative, then there's a term that is related to the expansion of the universe. That's just the number density goes down as the universe expands because of the volume effect. That's what this term says. Then there's this interaction term. So there's a cross section, just like before. And then there are these two terms here, n squared and the equilibrium number density squared. And the reason why they appear is just that every time you change the number density of this particle, you're assuming that it annihilates with its corresponding antiparticle, which is assumed in this case to have the same number density, just for simplicity. Now, of course, you can also have the inverse process where from the background medium, which is assumed to be in full thermal equilibrium, you pair create. And you can see that if the number density is higher than the equilibrium number density, this term becomes positive and there's a minus sign, and that means you start to get rid of particles. And conversely, if the number density is lower, you create particles. Now, this equation is typically, in most cases, not directly analytically solvable, but it's very easy to solve numerically. The trick in this case is always to calculate this term here, which can be super nasty depending on the theory that you're looking at. So let's I wanted to, yeah, let's see. Let's say that we are looking at a particle with normal weak interactions. What happens to that particle? Well, if the mass is very high, this particle actually stays in equilibrium until very late, until m divided by temperatures of order 20. And that means this so-called Boltzmann suppression, you remember this e to the minus m divided by t factor, that becomes extremely small. So you really very efficiently get rid of these particles. And that seems interesting because before we saw that the contribution to the energy density becomes too large if the mass is high. However, now it seems that we can get rid of these particles by pair annihilating them depending on what the mass is. And therefore, you might actually get a reasonable dark matter candidate somewhere for very high masses. And it's definitely worth checking out. You can do this calculation. Again, I won't bore you with the details, but the point is that what you find is that the final number density of these particles actually scales inversely with the cross-section. So the larger the cross-section, the more efficient you get rid of these particles. And therefore, the final number density actually goes down. So this is like the standard WIMP plot, which of course also works for very massive neutrinos. As you increase the cross-section, what happens? Well, neutrinos early on, remember time flows to the right in this diagram. Early on, you see particles are massless. Then it reaches the point where they become massive relative to temperature. The number density in equilibrium goes down exponentially fast. But at some point, you cannot keep equilibrium anymore. And then number is a conserved quantity. And that means that number divided by the photon number density goes to a constant. And this constant depends on the magnitude of the cross-section. And then you calculate the cross-section for a Dirac neutrino. What you find is that it just scales as the square of the mass of the neutrino. And in any case, the point is that as you go to larger masses, you have less particles around. And that actually means that you find that the final contribution to omega goes as 1 divided by mass squared. And we can put everything together here. And we can see that as a function of the mass, first, we have very little contribution to the energy density. Then we hit the critical point where we contribute too much. All of this is excluded, and then at some point it goes down again until it reaches this point where it would actually be a viable dark matter candidate. And of course, we know that these massive neutrinos are not a viable dark matter candidate because they don't exist. So that's a drawback, right? We know from old lab data that below 45 GeV, we have exactly 3 neutrino species from missing transverse momentum measurements. And that means that we would have, in order to be consistent and of course, forgetting about all possible decay channels and so on, we would have to go out here for it to be allowed. And that would contribute way too little energy density. But it sort of provides you with the prototype for how you should build a WIMP-like dark matter candidate. What you need to do is to go to a higher mass. And in order to get the right energy density, you need to have more of these particles around than neutrinos. How do you have more particles around? You make the cross-section smaller. So you need a particle that has smaller than weak cross-section in order to do this. So that's sort of your prototype for how you would want to construct a WIMP-like dark matter candidate. One thing that I haven't said, but which is actually an interesting point, that is that I've always talked about here the Fermi interaction. And of course, we know that the Fermi interaction is not a proper description of neutrinos when you go to higher energy, right? You need a renormalizable theory, electroweak theory. And the cross-section does not scale as energy squared in the full theory. When you go to high energy, it scales as energy to the -2. And if the cross-section drops with energy, then you can just extrapolate to higher and higher and higher energy. Then you find that neutrinos were out of thermal equilibrium in the super duper early universe. If you go to 10 to the 15 or 16 GeV, neutrinos were actually out of thermal equilibrium. You cannot equilibrate them in any way using standard model. Of course, that's not a major concern because we know the standard model is not the proper description of the universe at that high energy, but it's at least is interesting in the sense that if you have a theory where you have a light mediator, not a heavy mediator like the W or Z particle, but a light mediator, then the cross sections become very different. And actually in some beyond standard model theories, you could actually start to build up light particles very late in the evolution of the universe if they are associated with massless propagators and they're very light particles. So rather than having this idea that the universe was always in equilibrium early on, and then it drops out of equilibrium, you can actually have the completely opposite case. You can start from something that is out of equilibrium, and then as time progresses, it actually is able to build up an equilibrium distribution of whatever particle you're interested in. So that's quite intriguing, and it leads to some funny phenomenology and also in neutrino physics related models. Okay, so we still have a few minutes. I think I'm maybe spending a little bit more time than I should have. But how do you actually go about probing neutrino physics? So now we've set the stage. We more or less know all there is to know about standard model neutrinos and the early universe. Now you'd want to figure out how to probe it. And historically, the way to probe neutrino physics in cosmology was using interactions where neutrinos are important. And that's Big Bang nucleosynthesis. That's stuff that happens at the MeV scale. So if we do nucleosynthesis, we have one central parameter in the standard model. That's the baryon asymmetry, which is related to the baryon abundance in the current universe using this expression here. So for us here, it's just a parameter, right? We don't care about the origin. It's just a parameter related to late time behavior. Now, what happens in the universe if we go to, say, the 100 MeV scale, just after the QCD phase transition? So we have all the baryons are essentially in pions, and then there are, of course, some in protons and neutrons and so on. As you lower the temperature, every other particle, the neutrons and protons, vanish from the system. And neutrons are unstable, but on a much longer time scale, because remember, at 1 MeV, the universe is 1 second old. And therefore, the neutron lifetime of 880 seconds is very long compared to this. Now, interactions that keep the equilibrium between neutrons and protons, they're the weak interactions, assuming they are present and equilibrate the system. There's a relation between the neutron number density and the proton number density, which is quite simple. However, of course, it depends on weak interaction equilibrium. And that means that below the MeV scale, this decouples. Actually, it happens at around 0.8 MeV, roughly. And below that, neutrons, and the ratio is conserved except for out of equilibrium decay of neutrons. And eventually, of course, all the neutrons would disappear. But before that happens, deuterium starts to form once we go to 0.1 MeV roughly. And very quickly, everything is processed essentially into helium-4. So that's the basics of Big Bang nucleosynthesis. It doesn't go beyond helium-4 because there are no stable nuclei with mass numbers 5 or 8, because the alpha particle is so tightly bound. And unlike in a star, for example, you can't circumvent this by doing the triple alpha process because the number density is very low and you have very little time available. And therefore, essentially, BBN stops at helium-4, except for a very, very little amount of lithium and beryllium. So here you can see a typical ppn calculation as a function of temperature. We have first deuterium building up, then that burns into helium-4, and eventually almost everything is in helium-4. And one thing that is interesting, and which people noticed back in the 70s, is that when you change the baryon abundance, you actually change the number densities of various of these particles. And that means that by doing a precision measurement of, for example, the helium abundance, you should be able to infer the baryon abundance of the universe. So that seems quite nice. And the reason why you see here, for example, that it changes is it's a very small change. But the reason that helium-4 changes is simply that if you have more baryons around, ppn is able to start a little bit earlier. When it starts a little bit earlier, there are more neutrons around. Almost all neutrons end up in helium-4. And therefore, if you start earlier, you end up with more helium-4. That's why you get this positive correlation. However, of course, if you have more helium-4, you also more efficiently burn deuterium. And that leaves you with actually less deuterium and helium-3 because they are intermediate steps towards this helium-4 production. Lithium is more complicated also from an observational point of view, so I'm not going to say anything else about that. Yes, okay, so we can measure helium-4. And the idea always was, and I know I'm sort of out of time and we'll just continue this. Okay. Okay, so with helium-4, and I think this is a nice example of why you should be sometimes careful about cosmological observations. Of course, I'm more these days. I'm more a cosmologist than a particle physicist, but I would say that you should definitely be aware that there are many, many caveats in many of these observations. So helium-4, how do you measure the Big Bang abundance of helium-4? Well, helium is a very stable nucleus, and therefore, statistically, over time, you always produce more and more helium in the universe. So the idea would be to measure pristine material, basically material that has never been processed. And that could, for example, be in extragalactic H2 ionized hydrogen regions. And you would get something like this. There are many of these observations. So the idea is that the ppn abundance should be over here to the left. This is a parameter called the metallicity, strange astro parameter, but it basically tells you that over here we have processed material, meaning material that has been through stellar evolution. Over here we have pristine material, and this is what you're after. This is a nice study in sociology, I think. So this was a figure that Gary Steigman made a long time ago. But what you can see is that as a function of the year where the work is published, there's an estimated helium abundance measured. And as you might be able to see, if you go back to the 90s, back when I was a PhD student, there were two schools, basically. One which favored a low helium abundance, that was Keith Olive and collaborators, and another one, Isotov and Tuan, which favored a high helium abundance. Then they sort of merged. But what happened here? What happened here was that the first WMAP data became available. The WMAP data measures the baryon abundance with ridiculous precision compared to what BBN can do. Once you know the baryon abundance, you can use a simple BBN code to calculate what is the helium abundance. Then you get this. And lo and behold, all of a sudden, within a year, this is new BBN helium measurement, right? So all of a sudden, it jumps by a very, very significant amount. And then it sort of maybe has shrunk a little bit. And actually, if we go over here to the present day, the value measured by the Planck satellite would be thinner than one of the dashed lines here. So the point is that sometimes you should be a little bit careful about over-interpreting these results, right? So this systematic errors in this type of measurements are quite large, actually, and they remain so to this day. So in my opinion, this is a little bit more for historical interest than current interest. But of course, as you'll see tomorrow, we don't have time to go through it today, but as we'll see tomorrow, I'll start out with that. In many models of beyond standard model physics, you could actually fiddle around with, for example, the helium abundance without ever coming into conflict with anything related to the CMB. So it's not that BBN has become obsolete. It's just that for standard model neutrinos, it's no longer the best way of measuring things. So it's more reduced to a probe of beyond standard model physics in the early universe. Okay, let me stop here and then, yep.
Thank you, Steen.
Yep.
Are there questions?
Thanks. I think I have a very basic question. So when we're looking at the equation rho total equals rho matter plus rho radiation plus rho lambda,
Yes.
what do we mean by matter and radiation there? Is it things that are moving around and things that are not moving around?
It's a good question. So what I mean by matter and radiation is that if you write out the stress energy tensor in this system, in a homogeneous and isotropic universe, it has this nice diagonal form where you have the energy density and you have the local pressure. So what I mean by the distinction between matter and radiation relates to the pressure in that gas. So it's not something that moves in a collective sense, which would imply a violation of homogeneity and isotropy and structure formation. This is, if you look at a blob of matter and you look at the momentum distribution, then radiation corresponds to mass-less particles, where the only term in the dispersion relation is the momentum term. Matter, by definition, refers to the opposite case, where the rest mass is the only term.
Okay.
And of course, all particles in the standard model behave as matter or radiation. It just depends on when you look at them, right? So normally, for particles that are in equilibrium, particles disappear when they become non-relativistic, and therefore they are uninteresting from the point of view of cosmic expansion. However, of course, that's not exactly true for baryons, as we know, because there's the small baryon asymmetry that protects the baryons from this Boltzmann suppression. And therefore, eventually, they do become important, and the rest mass term does become important in that case.
Thanks.
Yeah.
Any other questions? There will also be like a session tomorrow in the evening where we can also discuss other
Yes.
questions. I had one question. So when you talked about the Boltzmann equations, you had these elastic and inelastic terms.
Yes.
You said that the elastic terms are always active, but if that was the case, the neutrinos would have the same temperature as the CMB.
Yes. Okay. So I didn't say they are always, but I say they are typically dominant. And if you look at this WIMP calculation, they are dominant by orders of magnitude. If you look at neutrinos, it's different, right? Elastic terms are still more important, but only by a factor of 2 or so than inelastic collisions for the light neutrinos. Yeah. And there you have to take all of them into account, yes. Yeah. So it depends on the setting.
Okay, I don't see other questions online, Mauricio? No? Okay, then let's thank Steen again. And we have a lunch break until 1:30. And I hope the lunch arrives.